Good morning. I'm Joseph Aya from the University of North Texas, and today I'm going to talk about what are n functions and why are they interesting. So first, we need to know about sets of measure 0. So it turns out that any finite set is a set of measure 0, and actually any countable set is a set of measure 0. So the rational numbers, for example, are a set of measure 0. But more generally, a set of measure 0 is one where it's contained in the union of a countable number of open intervals. And if you add up the lengths of all of those intervals, you can make that as small as you like. So as I said, any countable set has measure 0, and the Cantor set has measure 0. So you may have heard of the Cantor set, which is obtained by first removing the interval 1/3 to 2/3 from the unit interval, and then 1/9 to 2/9, and then 7/9 to 8/9. And if you continue in this way, at the end of this process, what remains is the Cantor set. And it turns out that it is a set of measure 0. So now something which is not a set of measure 0 is, say, the interval AB, where A is strictly less than B. That's not a set of measure 0. Okay, so what's an n function? Well, an n function is a function that maps sets of measure 0 to sets of measure 0. Now, it turns out that any absolutely continuous function is an n function. And also another example is if you have a differentiable function except on a countable set, that also turns out to be an n function. Now something which is not an n function is this thing called the Cantor function. So that's obtained by the following process. You remove, so on this interval from 1/3 to 2/3, you define the function to be a half. On 1/9 to 2/9, you define it to be a fourth. On 7/9, 8/9, you define it to be 3/4. And you continue in this way, and what you end up getting is a nice non-decreasing continuous function, and it actually maps the Cantor set onto the interval 0, 1. So anyway, the Cantor function here is not an n function because it maps the Cantor set, which is a set of measure 0, onto a set of not measure 0. Okay, so anyway, so that's not an n function. Okay, so what's true about n functions? Well, here's one thing. Let's say you have a measurable function, and let's say it maps measurable sets to measurable sets. Then this turns out to be an n function. So suppose not. So then that means that there's a set of measure 0, t, such that f of t is not a set of measure 0. So I have a little drawing over here. So this f of t has, say, positive measure. Now, one thing that's true is that if you have a set of positive measure, you can always find a non-measurable subset of it. So I denoted that as S. So then if you pull this back and intersect it with t, you get this new set, and it's a subset of t. So this set has measure 0, but when we hit it with f and bring it over here, we get the set S, which is a non-measurable set. But we were assuming that f mapped measurable sets to measurable sets. So anyway, so that's a contradiction. So it must be the case if a function maps measurable sets to measurable sets, then it's an n function. Now, interestingly, the converse is also true. So if you have a measurable function which is an n function, then in fact it maps measurable sets to measurable sets. So how can you see that? Well, take a measurable subset of AB, then it turns out that you can always find a compact subset Cn of f, such that f is continuous on this compact subset, and that's almost the entire set f. So you can make this measure here as small as you like. This is known as Lucin's theorem. Anyway, so you can do this for each n, and you can make it so that these fn's are an increasing sequence of sets. And anyway, then when you union all of these up and subtract from f, you get a set T, which is a set of measure 0. So you can always write your measurable set f as a union of these fn's, where these fn's are compact, and T is a set of measure 0. So then if you apply the function f to this, then you get the union of little f of capital Fn, and then union f of t. So here we were assuming that f was an n function, so this f of t is a set of measure 0, and f is continuous on each of the fn's. So f of the fn's is another compact set, and every compact set is measurable. So therefore, little f of capital F must be measurable. So we see that these n functions are precisely those measurable functions that map measurable sets to measurable sets. Okay, so now it turns out that there's a similar theorem here about continuous functions. If you have a function that maps measurable sets to measurable sets, if and only if f is an n function. Now, there's another interesting theorem about n functions, and it's this one, this Banach-Zariski theorem, which says that f is absolutely continuous on AB if and only if f is continuous of bounded variation and an n function. So now one of these implications we kind of already have alluded to. If f is absolutely continuous, then it is an n function. I mentioned that earlier. And then also every absolutely continuous function is continuous, and it's also of bounded variation. Anyway, so let's talk about the converse of this. So the converse proceeds as follows. So take an arbitrary closed interval here of the set AB. So since f is of bounded variation, then f is differentiable almost everywhere. And so you can write the set AJ/BJ as A union B, where f is differentiable on all of B, and A is a set of measure 0. So now, so f of AJ/BJ is going to be f of A union f of B, and now since f is an n function, then f of A has measure 0. Now, also another result which is true from measure theory is that the measure of f of B turns out to be less than or equal to the integral over B of the function f prime, the absolute value of f prime. And then B is a subset of AJ/BJ. So we get this inequality here. The measure of f of B is less than the integral from AJ to BJ of f prime. So anyway, then the measure of f of AJ/BJ, so f here is continuous. So this is going to be a nice compact set, and f of BJ minus f of AJ is going to be less than or equal to this. So anyway, we get this inequality, f of BJ minus f of AJ is less than or equal to this integral. And so then if we sum both sides finitely, then we obtain this inequality 1. Now, it's known that if you have a function which is where the first derivative is integrable, then if you have any, so then here we can make this right-hand side here as small as we like, as long as we choose the union of these sets AJ, BJ to have length less than delta. So anyway, so if E is a union of these finite set of intervals where the sum of the lengths of these is less than delta, then the sum of the f of bj minus f of aj is going to be less than epsilon. So that means that f is absolutely continuous. So anyway, so this project came up because I was working with a graduate student and we came across this topic in the textbook by Stromberg, Intro to Classical Analysis. And anyway, I had heard of n functions and some other people had not either. It seemed like an interesting topic. But anyway, so thank you for listening. Thanks.